Alright, this video is meant to help us understand or sort of expand our understanding of linear systems of equations. The three graphs that you see on the screen are three different types or three different sort of formations of linear equations that can happen. If we have two lines, the blue line and the red line, they can do any one of three things. The most common, or what we enjoy the most because we get a nice clean answer, is the graph in the middle, where those two equations are crossing at one coordinate. So you'll notice on this graph, assuming we were counting by ones, they're crossing at this point right here, which means the solution to our system would essentially be -2, +2, or the coordinate you see on the screen. Now, that's a fairly common thing to sort of learn to solve for systems to initially begin with. But remember that two lines don't necessarily have to cross. Remember that two lines can be also parallel, such as the two lines on the left. If two lines are parallel and they never cross, then there's no one point that makes both lines true or both equations true. In that case, we say that there is no solution. We can't write down a coordinate because there's no coordinate that would be on both lines. The reason for that, again, is parallel lines. And the biggest thing we want to identify is when we're looking at those two equations of those lines, what do two equations of parallel lines have in common? And the big thing you want to remember is that all parallel lines have the same slope, but they have to have different y-intercepts, so they need to start in different places. So if we were in y equals mx plus b, we would look at those slopes. If they're equal, we'd also double check the y-intercepts and make sure they're different. The problem is, if they have the same slope, but they have the same y-intercept, then we get the two lines over here at the right. The blue line and the red line are essentially on top of each other. They're both starting in the same place, but they also exist in the same place everywhere along the graph, everywhere along the x-axis, everywhere throughout the domain. In that case, again, we say that there's many solutions to our system because they're the same line. Every point that's on the red line is on the blue line, and therefore every point that's on those lines is a solution to the system. So the best that we can do is just say that there are many solutions. Again, to identify that, they're not parallel lines, but they will have the same slope as well as the same y-intercept. They're starting in the same place and they're traveling in the same direction. Both of those things will be the same. Now, it's easy to identify when we're graphing whether things are parallel or look at the same line. But again, algebraically, that's going to look a little bit different. If we have a system of equations, such as the one on the left, 2x plus y equals 5 and -2x minus y equals -1, those are definitely two different equations. Okay? But notice if we try to use the method of elimination to solve them, 2x plus -2x and y plus -y, basically that entire left side will turn to 0. But 5 plus -1 becomes 4, and we get the statement 0 equals 4. Well, as we know, 0 does not ever equal 4, and because that statement can never happen, it means that the solution to this system can't exist. Or basically, that's algebraically what a solution with, or what a system with no solution will look like. So we would just say, get this to participate here, to work with me, we would just say that this solution is never true, therefore there is no solution. Graphically, again, that means that these must have been parallel lines. If we take the two equations down here at the bottom, and we went ahead and solved for y, in the first equation I'm going to subtract 2x, which means start at 5 with a slope of -2. I would graph that red line. In the equation at the right, I would add 2x to the other side, and then also divide by a -1, meaning start at +1 on the y-axis with a slope of -2 again. Notice the same slopes, -2 on both lines, but different y-intercepts, 5 and 1, making these two lines parallel, and thus having no solution. On the next page, we have a couple of systems here. Go ahead and take a minute and pause the video. Solve those two systems. You can pick either substitution or linear combination, the elimination method. Either method should work. but see what it looks like and see if you get a solution. See if there's one solution, many solutions, or no solutions to our system. Go ahead and pause the video now, and I'll put up the answers in just a minute. All right, we got the solutions to both systems here. Over at the left, you'll notice that we solved by elimination. I noticed that I was lined up x's, y's, and constants, all in nice columns, both in standard form. Great time to do elimination. However, -2 and -4, or 1 and 2, they weren't going to cancel on their own. So I multiplied the top equation by -2, causing that to be a +4, minus a 2y, and again, 3 times -2 would be -6. Adding that second equation to our new green equation here, -4x plus 4x is 0, but also 2y plus -2y is 0. The entire left side disappeared, became 0. Because our variable is eliminated, I already knew it was either going to be many solutions or no solution. That's what always happens on those many and none kind of situations. On the right side is what's going to determine which of those two it is. 6 plus -6 also turns to 0, which means unlike the example on the previous screen, 0 is always equal to 0. That's always true. And if that equation is always true, then our system will always be true. If we have a point that's on one line, we're guaranteed it'll always be on the other line, which is why we get many solutions. These two equations represent the same line. Over here at the right, again, I noticed I was solved for x in the second equation, so I substituted instead of being linear combinations. A great time to substitute. So 6 times x being -4y plus 2. Right? Take out x, substitute in what it's equal to. Then I continued with -12y equals 30, distributing the 6, then adding like terms to make -36y, followed by subtracting 12. 30 minus 12 makes 18, and dividing by -36 made a -1/2. Plugging my -1/2 into my equation, -4 times -1/2 is +2. 2 plus 2 made 4. And our final coordinate, not a many and not a none kind of a situation, because our variables didn't completely eliminate, because one variable still exists in our equation all the way throughout, we came up with one solution to our system. These are two lines that crossed at the point 4 and -0.5. Again, there's 3 possible situations that can happen, so just be prepared for what kind of an answer you're going to receive. There can be one solution, like our last example. We can have many solutions, or a system that's always true for any point that's on one of the two lines. And we can also have no solution. If we eliminate our variables, both of them disappear, but we get a false statement, then we end up with no solution because of those parallel lines. I hope that helps you understand special systems of equations, such as many solutions and no solution, as well as a little more understanding of that single solution idea. If you have any other questions, make sure you talk to your math teacher. Otherwise, good luck, have a great day, and of course, have fun.